Okay. Yeah, as Shayak mentioned, I did my PhD at Professor Vidya Madhavan's group, and I recently started as a postdoc in Professor Amir Yacobi's group a few months ago. But today I'm going to talk about some of my PhD work on UTe2 and talk about this strange magnetic field-dependent charge density waves that we discovered in the material. For people who are sort of not tracking the field of UTe2, here's a brief timeline for them. So a quick digging into the scientific literature reveals this interesting timeline where the first powdered UTe2 was synthesized in the 60s and 70s. However, we did not see any characterization on this material until the 1970s or 80s. And the characterization stopped at liquid helium temperatures. It was only in the 1990 and early 2000 when the first single crystals of UTe2 were discovered. We saw some magnetic characterization and even resistivity, but all the measurements stopped at 2 Kelvin. However, it was only in 2018 when Sheng Ran and colleagues actually synthesized this material and cooled it down to very low temperatures that they discovered superconductivity. This is probably both to do with technological advancement and also perfecting the growth recipe and the stoichiometry of uranium and tellurium, which seems to be important in this material. Anyway, so after 2018, after the discovery of superconductivity in this material, this opened this Pandora's box of experimental enigmas that I'll briefly go over. So some of the key highlights are as follows. In normal state, uranium ditelluride is a heavy fermion paramagnetic metal. So the resistivity is pretty anisotropic in all three directions. The resistivity drops along the B and C direction after the onset of the Kondo coherent state, which is around 30 Kelvin. However, the C-axis resistivity has this strange upturn much below the Kondo temperature, and I think it's still not clear what the origin of this is. Similarly, susceptibility and μSR measurements show no magnetic ordering down to the lowest temperatures. So it's believed that UTe2 is a kind of this paramagnetic end of this ferromagnetic series of uranium compounds where we have ferromagnetic fluctuations and superconductivity coexisting, which has given rise to this theory of probably harboring triplet superconductivity. But all's not well because some recent inelastic neutron scattering measurements found antiferromagnetic fluctuations, which are kind of correlated to superconductivity. So it's still not clear which one of these plays a major role. ARPES measurements found quasi one-dimensional bands in originating from uranium and tellurium. However, the more interesting properties of UTe2 are in its superconducting state. So some initial samples of 2018 found that the TC was 1.6, but however, when people perfected their recipe, it could be pushed to 2 Kelvin for some more recent samples. So specific heat shows a large jump and a large residual Sommerfeld coefficient, which indicates quasi-particles in the superconducting state. This Sommerfeld coefficient is also tied to the TC and the sample quality as we expect. So it goes down in some more recent samples, but doesn't go all the way to zero. The more convincing argument for spin triplet superconductivity comes from night shift measurements where people saw that the night shift does not drop by a lot. It drops barely by 0.05% across TC, and this has been verified by multiple groups in the world across multiple samples. Similarly, the magnetic field, the HC2 measurements are extremely anisotropic in all three directions. In the B direction, the critical field is pretty large. It can probably go around 40 Tesla, which shows some unconventional pairing mechanism already. So talking about the order parameter, I think it's still kind of unclear whether it's a single or multi-component order parameter. Some initial measurements showed broken time reversal symmetry in Kerr effect, and double jump in specific heat, pointing towards a multiple component order parameter. But some more recent samples from Priscilla Rosa's group saw only a single jump at specific heat. Similarly, thermal conductivity measurements indicate a nodal order parameter, probably with nodes along the A direction. So it also exhibits a rich phase diagram in magnetic field. There are multiple re-entrant superconducting phases and field polarized superconducting phases. So let me see if I can use my pointer. So can you see my pointer? Okay, so this is the B direction where we see that there's a re-entrant superconducting phase that exists up to 40 Tesla. And the field polarized state, which is along this strange direction. So this is the 0-1-1 direction. This is important because when we try to cleave this material, it actually cleaves along the 0-1-1 direction. So if we apply a magnetic field along the 0-1-1 direction, we see that superconductivity is suppressed around 10 Tesla. And then as you keep increasing it, it reappears around 45 and then exists till like 60 Tesla. It's crazy. So similarly, pressure-dependent measurements show multiple superconducting states. Even new magnetic phases appear. So there's still a lot of interest on what's going on in UTe2. Previous STM work from our group, which was not done by me, but by a former postdoc, Lin Zhao, shows signs of a chiral superconducting order parameter. So here's what they did. So low energy spectroscopy shows this very familiar Fano line shape, which generally happens when we have a resonance in the system. And this resonance is the Kondo coherent state in UTe2. So this, if you fit it, you will get a Kondo temperature that agrees with transport measurements. Now, if you zoom in into close to the Fermi energy, we find an extremely shallow superconducting gap. It barely suppresses by 10% at 270 millikelvin. However, the interesting observation is when you go to step edges in this material, you see a state inside the superconducting gap that seems to be knowing what step you're actually measuring the spectra on. So it has this strange particle hole asymmetric shape on opposite step edges. I don't think there's a clear understanding behind why the shape is this way, but all we know is that this is tied to the superconducting state, because as you increase magnetic field and go to around HC2, it becomes undetectable. Okay, so to briefly recap, some general characteristics of heavy fermion superconductors are the Cooper pairs are formed from heavy quasiparticles. It exhibits large upper critical fields and short coherence lengths, and there are line or point nodes in superconducting gaps. So all of these have kind of been seen in UTe2. Now, something else is also expected, like you can have a nearby charge ordered phase or a modulating superconducting state like a pair density wave state arising from strong correlations. So can we see an coexisting charge order? So STM is a great tool to visualize additional orders like this, because we can actually see CDWs, which is charge density wave, or PDWs, or pair density wave, both in real space and momentum space with very good resolution. So before I go on to experimental results, I'll just quickly talk about the technique of STM. I'm pretty sure everyone's familiar with it. So we have this metallic tip that we bring in close contact with the sample at a specific bias. There's quantum tunneling of electrons that allows us to measure topography with very nice atomic resolution. We can also measure density of states by taking a derivative of the tunneling current with respect to bias. So this is, for example, a spectra measured on bare niobium. We can also do something else, which is take spectra at different positions in real space and then map it out as a function of energy. So this gives us a three-dimensional data set where at each energy, we have like a snapshot of the real space. And if we translate that into Fourier space, we can get information about quasi-particle interference, band structure, and so on. So coming back to UTe2, UTe2 has this body-centered orthorhombic crystal structure where there are two different kinds of tellurium. They're different because the bond length between the U and Te is slightly different for two of these atoms. The uranium forms this two-legged ladder structure that goes along the A direction. So this is the like the two parts of the ladder. And then when we try to cleave it in STM, it cleaves along this strange plane, which is shown by this pink rectangle. This is the 0, 1, 1 facet, and that reveals this big, beautiful terraces of 0, 1, 1. If we take a close look, we can see that we're seeing two kinds of atoms. One is brighter than the other. So that is because the tellurium 1, which is the darker one, is slightly, I guess, projected to the surface than the tellurium 2, which is the blue one. And based on this, we can identify the positions of the tellurium, and the uranium is underneath, so we don't actually see it. And the tellurium orbitals are also slightly bigger. So we mostly see the tellurium atoms. And for people who are interested, this also gives us access to the orthorhombic 0, 1, 1 facet of the Brillouin zone. Now, we can also look at this surface in the Fourier space. So I have rotated the topography. So the chains are along this direction, and this is the crystallographic A direction. So this is a topography taken at 300 millikelvin. And if I take a Fourier transform of this is what we see. So first of all, we see we can identify the Bragg peaks that originate from the atomic sites. This is a strange squished hexagonal shape, and that's because the lattice is also a bit strange. But however, apart from these lattice Bragg peaks, we see additional modulations which are at smaller Qs, which means they're larger in real space. And we can also visualize these Qs. We can also see that they're at the vertices of the Brillouin zone. So if we pick up this Q vector and do an inverse Fourier filtering, we can actually visualize these modulations in real space, and it's pretty long range ordered. We can see it in the inverse FFT. Now the question is this a charge density wave supermodulation? We can actually look at the density of states maps, as I said before, and see what the charges are doing. So this is what we did in the next part. So here's a topography, and we obtain density of states maps across different energies in this yellow rectangular region. So this is the Fano peak. So we can take a slice at Fermi energy, which is 0 millivolt, and we can see that the density of states actually oscillates quite a lot. But in Fourier space, we see that it corresponds to the same peaks that we saw in topography. We can also take a slice at the Fano peak, which is at -6 millivolt. And then we see that it also shows the same peaks as the topography. If we can also look at a very high resolution atomic scale density of states maps. And what we see is that almost every alternate tellurium atom lights up along the chain. The reason I say almost is going to become clear in the next slide. So we can track the position of these Q vectors as a function of energy. And what we see is that there's no dispersion, they're static. So this is direct indication that it is coming from static charge density wave oscillations and nothing like dispersion from quasi-particle interference that is also known to be done through STM studies. We can measure the magnitudes of these Q vectors, and we see that they're all three of them are incommensurate. And the reason it appeared like almost every atom is because they're pretty close to 0.5, which is half the lattice distance. So some of the symmetry relations between the CDW, and this will be important for the later part of the talk, is the yellow one, Q1, let's call it Q1, is related to the red by mirror symmetry, and Q3, which is the purple one, is related to both of them through a Bragg peak. So we can track these CDW as a function of temperature. So now I'm going to show FFTs of topographies and density of states maps as we increase temperature. So this is 300 millikelvin. This is 4.5, it's weak. And by 10, we see that this is gone. I have more recent data from, I think, a few months ago, where we actually tracked it more carefully. And it shows that the CDW becomes undetectable around 6 Kelvin. So this shows that it's a very low temperature charge ordered state. For comparison, charge density waves in common TMDs like tantalum disulfide, niobium diselenide, they have the critical temperature around like 30, 50, or 100 Kelvin. So such a low temperature charge ordered state already implies a slightly unconventional mechanism behind it. Anyway, so next we go on to track its field dependence. So in principle, we can apply perpendicular magnetic field with our STM, and in principle, it should not do much because we can only go to fields up to 10 to 11 Tesla. However, we did it anyway because there was nothing much to do after this. So now I'm going to show Fourier transform of topographies with increasing magnetic field below TC. So 5 Tesla, 7, it gets weaker. By 10, we see something strange happening. You can see that the CDW in the red square is pretty weak compared to the other two. And at 11 Tesla, it's the same level as the noise level. So it becomes undetectable. Now, as I said before, the red and the yellow are related by mirror symmetry. So we see that in presence of a magnetic field, the CDW is breaking mirror symmetry. But this is from the topography. So we want to see what the electrons are doing and if this mirror symmetry breaking is actually imprinted on the local density of states. So that's what we set out to do. Now I'm going to take line cuts in Fourier space as a function of energy at 10.5 Tesla. So these are the 3 plots. So you can see that in the red square, there's no signal from the CDW, which means that this mirror symmetry breaking is actually imprinted on the density of states. Some more line cuts show that all components of the CDW are kind of suppressed in magnetic field. However, one of them is much more suppressed than the other two. This is not very surprising because the magnetic field that we're applying is along this strange direction, and this magnetic field actually also breaks mirror symmetry. But what is surprising is that the CDW is responding to this magnetic field at such small fields. Now, this material is very three-dimensional, and the way we glue it and cleave it to study in STM, we can sometimes have tilts, and this is not controllable at the moment, but it's interesting because UTe2 has a very anisotropic magnetic field dependence, so it can give us more information about the material. So on one such sample, when we apply a magnetic field, what we see is that as we increase magnetic field below TC, all 3 components of the CDW are suppressed. You can see that this is 0, 5, 9, and 10. And by 10.5 Tesla, we can hardly detect the CDW. And we do not even detect it in density of states. So it's actually gone. So I can track the intensity of the peak, which is an indicator of the strength of the order parameter of the CDW as a function of increasing magnetic field, and it goes down like an order parameter. So what is interesting is that in this direction, if you look at resistivity, so this is 11-degree tilt on the sample, which means, so 23-degree is our actual direction because of this cleave plane, and if you add 11 to that, it's 34, and along that direction, the critical field is much smaller, which means that we can actually reach the critical field, and that's why we're seeing this suppression of the CDW. So what this means is that the CDW is killed as superconductivity is killed in this material. So there are 2 aspects to this study that are very strange in terms of what is known about CDWs. One is the directionality, and the other is its relation to superconductivity. So it's not normal for CDWs to respond to magnetic field. For example, take niobium diselenide, where you have a CDW and also the superconductivity. But when you kill superconductivity, you don't see the CDW disappearing. However, in some recent studies on these Kagome superconductors, people have seen that the high temperature CDW actually responds to magnetic field in this strange fashion where you can flip the chirality of the CDW, which is shown here, by flipping the direction of the magnetic field. However, this is not similar to what we are seeing, because in this case, there's prior evidence of time reversal symmetry breaking in magneto-optic Kerr effect, and the CDW persists above HC2, which is different for us. For us, the CDW dies above HC2. So then the question still remains, right? What is the possible origin of such an unconventional CDW in UTe2? So this is where our theory colleagues come in. So we have a proposal based on Ginzburg-Landau theory, which was developed by Julian Maiman and Professor Eduardo Fradkin at UIUC. The details of it can be found in our paper. The proposal is so the disappearance at HC2 shows that the CDW and superconductivity are connected. So what we propose is that the CDW is actually a daughter order from a pair-in-pair density wave state that coexists with uniform superconductivity in this material. And that given the evidence of a triplet order parameter, it's likely that the CDW inherits this triplet character, and that would naturally explain the direction sensitivity and the behavior in magnetic field. Oops, sorry. So what is nice is that subsequent experiments from Professor Seamus Davis's group using Josephson STM has actually detected these pair density waves. So in this experiment, they take a superconducting tip and look at a superconductor. And for them, the tip is made of niobium. So this is data from a normal tip where we see an extremely shallow gap. But when you look at it with a niobium tip, you can move the gap by delta 1 plus delta 2, and that's what this is. What they see is that in density of states maps, they can see this delta delta is basically the oscillation of the gap size in real space. And if you take a Fourier transform of the oscillation of the gap size, you can see that it oscillates at the same Qs as what we see in our measurement. So this is actually direct evidence of the existence of a pair density wave in UTe2 with the same Q vectors as the CDW. So one question we can ask at this point is, based on our model, what do we expect to happen in the presence of a magnetic field? So in a usual type 2 superconductor, when we apply a magnetic field, we can punch holes in the superconducting order parameter and have vortices where the order parameter winds by 2 pi. So inside the core of the vortex, the amplitude of the superconducting order parameter goes to 0, and the phase winds by 2 pi around the vortex. So this is like a topological defect. And then what do we expect if we have the CDW that is induced by a PDW based on our Ginzburg-Landau theory? So in that scenario, we would expect magnetic field to punch vortices in both the uniform component, which is delta naught, and the PDW component, which is delta Q. And that means we should have vortices in the CDW. And these vortices of the CDW are basically dislocations in the CDW where the phase of the CDW winds by 2 pi. So this is the expectation. And the question is, can we verify this? So we actually can, because the Fourier, we can use something called as Fourier space decomposition. So what we do is that in the Fourier space, we have information about both the amplitude of the CDW and the phase of the CDW in this fashion. So if we take a topography and the corresponding FFT, we can pick out a Q vector and look at its amplitude and phase independently. So I'll divide this into 3 parts. One is the amplitude, the other is the modulating component, and next is just the relative phase where we remove the Q information. So the amplitude looks as so. And this is the modulating component where we see Q and phi. Q is the modulation wave vector and phi is the relative phase. And if you just look at phi, then you see something like this. So this is at 0 Tesla. And what we see are these phase windings, which are very few in number, even at 0 Tesla. And if we take polar plots of that phase winding, what we see is that if you take a cut around 1, you see that the phase winds from minus pi to pi, which is like 2 pi. And then for the other one, it goes the other way. And if you take a region where the phase is pretty constant, we see a constant phase. And these phase windings are opposite in nature, so they go by plus minus 2 pi, and and we expect them to be confined to each other to minimize energy. So this is at 0 Tesla, where we do not expect a lot of vortices. Now let's look at what's happening in the amplitude as a function of magnetic field. So the first is a Fourier transform. We pick out this red signal, and this is the amplitude map in real space. And then the bottom panel is a histogram of the amplitude, with the red dashed line being the mean value. So as we increase energy, we see that the amplitude gets suppressed, and it gets suppressed non-uniformly. Like it's not the same image throughout getting dimmer. We see some pattern emerging here. And this can get clearer if we look at the relative phase. Now, if we look at the relative phase, we have, let's say, two dislocations to begin with. And as we increase magnetic field, we see increase in number of dislocations. And this is exactly what was predicted by the Ginzburg-Landau theory. What is more interesting is that if we map out regions of 0 amplitude, which is shown by this map here, so these are regions of 0 amplitude, and then find out the positions of the cores of this dislocation and perform a cross correlation of these two maps, we can see that there is one-to-one correspondence between the dislocation core and the regions of 0 amplitude. And what this indicates is that the way the CDW is getting suppressed is through the generation of these dislocations. And when the dislocations become enough in number, they kill long-range order. And this verifies the Ginzburg-Landau prediction. So in summary, this work reports the discovery of an incommensurate multi-component CDW in UTe2. The CDW breaks mirror symmetry, indicative of a possible triplet order parameter, and is suppressed at magnetic field. We observe the increasing number of dislocations with increasing magnetic field, which is consistent with the pair-in-pair density wave state in UTe2. However, there are still some open questions. One is because STM is extremely sensitive to the surface, the question is this a bulk order or a surface order? And this needs low temperature X-ray measurements, which are non-trivial because the CDW has a very low TC. Then what is the microscopic model behind such a CDW? And the final question is, why is the temperature of the CDW melting higher than the temperature of superconductivity reported in UTe2? So I think these are areas of active research at the moment, but there are no clear answers at this point. At the end, I want to thank members of my lab and the theory collaborators, Julian, Professor Fradkin, and Laime, and the material synthesis group at NIST and UMD for continuously supplying us with samples throughout these measurements, Shengran, Nick Butz, Shanta Shaha, and John Pierre Paglioni. And finally, I want to thank the funding sources for supporting me and the project during this time, NSF, Moore Foundation, and DOE. And if you have any other questions, I'll be happy to take them now.
Right. So thanks for a great talk. And yeah, do you have any questions?
Oh, hello, Anuva.
Hi, Keenan. Nice to see you.
Hey, you remember me? Thought I
Yes,
might
I
have
do.
caused enough trouble in Austin. Dumb question. Is this the only surface you can cleave in uranium telluride, or are there other surfaces that, oh, we can look at the CDW, PDW from a different direction?
Oh, that's a very good question. So, I have tried cleaving on other directions. I had, I think there were 2 samples out of all the samples that I studied where the surface did look different. But the issue is they're so small in size, it's just hard to tell if it's crystalline or just some random flake just came off. So it'll be very interesting to do that, but I haven't had any success so far. But I do know, I think someone from Seamus's group mentioned that they had once, out of all the samples, they had cleaved, managed to cleave in a different direction where it did not look chain-like, like the way we have, and had a different symmetry, but they were at 70 Kelvin. They couldn't do much. So yeah, no luck so far.
Thank you very much.
So, okay, I had a question about the vortices part.
Yeah.
So in those experiments, are you below the superconducting transition? Like
Yes.
it is
Below.
superconducting.
Yeah, yeah.
And I don't know. Do you see like normal superconducting vortices too at that time,
So
or
yeah, this is, I think every time I've given this talk, people have asked me this. The only problem in that is, I'll show you how the gap looks like. So this is, you see the scale here, it's going from 0.1 to 1.0 whatever,
right?
which means it's basically a 10% suppression. And if you take a line cut, even on a very clean area, you can see that the gap sometimes goes to 0 or goes to 20%. So the way we see vortices in STM is basically because you fill up states inside the superconducting gap, inside the vortex, and outside there is, it doesn't get filled up, so there's contrast. But now you can imagine that if your gap is already getting so affected by just the CDW and the PDW being there, if you have additional structure because of the vortex, you'll probably have a hard time seeing them. But this gap does go away with magnetic field, so which is why we know this is the superconducting gap. But just seeing the vortex lattice is extremely hard because of the shadow gap.
Becomes like a resolution issue, I guess, eventually.
Yes, yes. So maybe if someone has a dilution fridge with an STM, they can try to do it. And I'm not sure that it's going to help, because I think, so one of my old lab mates who was in China, they had a 80 millikelvin fridge, who got their hands on UTe2 somehow, but their gap also looked identical. So this is probably not a resolution issue. The reason the gap is shallow, it's probably something to do with UTe2 itself. But they never tried doing a vortex lattice. So
I love how you just nonchalantly said, oh, they somehow got their hands on uranium telluride somehow.
oh, I don't know. Sorry. I don't.
Yeah, that's, might have to plug a few leaks. Another silly question. Can you target individual vortices? I vaguely remember stories about possible Majorana fermions in the cores of P-wave vortices. I'm not sure if that's even been thought
So
of.
the maps that I showed before, they are dislocations of the CDW. So we don't know where the actual vortex of the superconductor is. So there's some argument based on Ginzburg-Landau theory that you can find in the preprint of the paper, where we say that if you want to minimize energy, you will have these vortices at different locations. But it needs to be verified experimentally. Okay.
Hi, thank you for the talk. So
Hi.
you mentioned that TC of CDW is larger than the superconducting one. Did
The
you
what?
try
TC, yes. Yes.
Did you try to apply the magnetic field in that regime of temperature where the CW is
Yes,
there, but
I
the
think
superconducting is not?
we did, and then another group recently did. So it doesn't seem to be affected. If you ask me, it's not going away. So it does look like it's not affected, but I think we need to do, or not me, whoever is the graduate student right now, needs to do more careful measurement. Yeah, because
Right.
remember that if you have the magnetic field exactly perpendicular, the TC is pretty high. Oh, the HC2 is pretty high to reach with our STM. If we have a tilted sample, only then we can reach the HC2, and then it goes away. So if you ask whether mirror symmetry breaks, if you apply perpendicular magnetic field at 1.7, it doesn't.
Thanks.
Yeah, I have a kind of related question, which you mentioned that this kind of theory understanding relies on a parent pair density wave, but I have trouble understanding how that works because your charge density wave survives for higher temperatures than superconductivity.
There's a problem there. The only explanation, so okay, the issue is it's not whether this is the only mechanism. The question is what else can it be, right? So one possible way that we thought of where we did not have to invoke the PDW scenario was, let's say there's a spin density wave, and then you can explain that the spin density wave goes away when you apply a magnetic field. But that case has issues because there is no reported spin density wave in several magnetic scattering experiments. So we cannot go through the spin density wave route. So one way we can sort of reconcile these two is, let's say if at the surface somehow the PDW survives above TC for a small range of temperature, that is something that transport would not be able to detect because they're primarily sensitive to the bulk, but it's still an open question.
And what was the fact that
T of PDW is somehow greater than T of uniform component, then maybe you can still have this situation.
couldn't you resolve that in STM?
No, the gap is at plus minus 250 micro EV, and that is delta naught plus delta PDW. So it's pretty hard to go smaller than that at 300 millikelvin. We do see some strange feature in spectra at an energy scale which would agree with the, so this is the Fano resonance at minus 6 or 5 MeV, but there's this change in slope here around minus 1 MeV, which would kind of agree, minus 1 to minus 0.7 MeV, which would kind of agree with the temperature scale of the CDW, 6-7 Kelvin. But honestly, we see the CDW across this entire range. So at every energy slice, the density of states oscillates. So I don't know. Don't have a good answer for you.
Thank you. You mentioned also something about the spin triplet nature of the order parameter being crucial for your kind of
so
vortex
that's
physics.
only crucial if you consider the difference between a perpendicular magnetic field versus a tilted magnetic field. So at 10 Tesla in a perpendicular magnetic field, the CDW kind of still survives, but in a tilted magnetic field, the CDW goes away. So what we expect is that if we had access to higher magnetic field along the perpendicular direction, then we would eventually reach HC2 and kill the CDW. Because if you look at transport here, I'll just go back to my slide. Here. So if you look at these two curves, compare the yellow and the gray, you can see that the HC2 is different for these two directions. One of them is slightly smaller than the other. So when you go to the direction, which is this one, which is slightly smaller, you can actually suppress the entire CDW. So if we had access to, let's say, 15 Tesla in STM, and we had a perfectly flat sample and apply a magnetic field, then probably we can also kill the CDW in that direction. So the suppression of the CDW is not dependent on the triplet character, but the dependence on direction is. I hope I have made myself
Yeah,
clear.
so I think maybe I didn't appreciate. So this you're saying at low temperature, the CDW and superconductivity are killed at the same field, right? But they're not killed at the same temperature, which is somehow
Yes.
even weirder.
Yes.
Okay.
Yes. That is the weird part.
Yeah.
Correct. Yeah. So I'm happy to discuss if someone has some other explanation that takes into account all the experimental observations and what we are seeing, but we have so far not been able to.
Right. Are there other questions or?
Can I ask just short
Yeah, go ahead.
question? Yeah, thanks for the talk. I was just wondering, apart from the temperature dependence of the charge density wave, is there any other experimental reasons why you think you're observing two different orders in uranium ditelluride?
What are the
So,
two orders? CDW and PDW?
Yeah.
So I guess two answers, right? One is the magnetic field dependence, which suppresses the CDW. The other is the Josephson tunneling experiment, where they see the gap being modulated at the same Q vector, like this one. So when you take
Sorry. Yeah, my question was, what are the reasons you think you are observing charge density wave, but not pair density wave?
Because we are at very high energies, not very high, we're much higher than the superconducting energy scale. So the superconductivity gap is like plus minus 250 micro EV. Okay. And this topography, for example, is at minus 20 MeV.
I see. So like 2 orders of magnitude difference.
Yes.
All right. Thank you.
So we don't have any more questions. Let's thank Anuva again for a great talk.
Thank you.
And I think we'll be back on 6th December with the next talk in this seminar series. See you all then.
Bye.